This is 7.2. And in 7.2, we take a look at a confidence interval for the mean of one sample. And the reason I'm highlighting this is because in the next section, we are going to look at the mean for two samples, okay? And then in the next section, we're going to look not at the mean, but at the proportion of one sample. And then we're going to look at the proportion of two samples. And all four of these have the same essential mathematical structure. The procedure that we follow is going to be the same for all four. We're just going to make slight tweaks to each one, okay? So this section really establishes the foundation for the mathematics that we're going to use for the next four sections. So here we go. How do we find this margin of error? Because the point estimator for a mean is actually pretty easy. Remember, the point estimator is from the sample. So how do you find the mean from a sample? You just add them up and divide by how many there are, right? Or you use a formula in a spreadsheet. So you copy and paste your data into a spreadsheet and you type equals average and you find the mean. So that's easy. Finding the point estimator is easy. And that is going to be this number. Okay, that's X bar. So this is the sample mean. Okay, the sample mean, the average of the sample. Okay, the next part is how do we find this margin of error? Because remember, we're going to take our mean, X bar, and we're going to add the margin of error, and that's going to be our upper boundary. And then we're going to subtract the margin of error, and that will be our lower boundary. Okay, so that's the idea. So how do we find this margin of error? So there's two ways we have to do this, unfortunately. So method number one, this is the easier of the two. So method number one is if your sample is larger than 30. So remember last section we talked about having samples larger than 30. If your sample is larger than 30, then you can say that it is normally distributed, and we can calculate this margin of error using a z-score. Okay, great. This is what we've been doing for the last chapter. So your margin of error is equal to this formula. Here's your z-score right there. So you find the z-score, and then you also calculate this value. And this value should be familiar. Remember, this came from 6.5. This was the sample mean standard deviation. Remember that? Where you took the standard deviation from the population and divided by the square root of how many items there were. That was our modified standard deviation. Well, that number pops up here. So you take the z-score for your confidence interval and you multiply it by this modified standard deviation. And that's it. You're done. That is your margin of error. Okay? So that's the easy part. The tough part is when you have a small sample where the number of items in your sample is less than 30. Now, when you have a sample that is less than 30, it's not normally distributed. You can't say it's normally distributed. You can't say that the sample mean is normally distributed. Instead, what happens is you get something like this. So if I were to draw a graph, and let's say this red line is the standard normal distribution, okay? If your n is less than 30, let's say n is equal to, and I want to do this in a different color. Whoops. Let's say that n is equal to 20, okay? When you have an n equal to 20, this standard deviation or this normal distribution curve gets modified. It gets a little bit deformed. It gets squashed down in the top and the tails get kicked up. Now, because of that, it changes the area. And so we have to find a different way of finding the area. We can't just use a z-score anymore. And if n becomes even smaller, let's say n equals 5, the graph becomes even more deformed. So it gets squished down even more at the mean gets squished down and the tails get kicked up even more. And now the area is very, very skewed from the normal distribution, okay? So how much the normal curve, this normal distribution, is deformed is based on an idea called degrees of freedom. And instead of using a z-score, we use something called a t-score. And I know you're thinking, what, like one more variable that doesn't make any sense. This is called the student's t-distribution. And I don't know why they call it the student's t-distribution. That's what it's called. But what you do is you go out and you find this t-score, and we're going to show you how to do that in just a little bit. And then you take the standard deviation from your sample and you divide it by the number of items there are. So this is familiar. This is something that you've seen before. The t-score, it's what's different. So how do you find this t-score? So the t-score is based on the degrees of freedom. And the best way to explain the degrees, by the way, degrees of freedom is just the number of items minus one. Number of items minus one. So the best way to explain this is if you have 5 people and 5 chairs, the first 4 people get to choose what chair they want to sit in, right? The first person has 5 chairs to pick from, so they sit in one of them. And then the next person has 4 chairs to pick from. They can sit in one of them. But the last person has no degree of freedom to pick what chair they want to sit in. There's only one chair left. That's what they get. So if you have 5 people, there are only 4 degrees of freedom because the last person doesn't get to pick, okay? So what you do is you take the degrees of freedom from your sample. So if you have 20 people, if n is equal to 20, then the degrees of freedom are equal to 19. And that dictates the shape of the normal distribution that you're going to use. And then from there, you can look up the area on the student t distribution. We're not going to do that. We're going to use Desmos and a Google Sheet to do this instead of looking it up on a table. But we got to explain it this way. So here's what I just described. If you look at this graph over here, this is n equals 30. So if you've got 30 people, you have the red graph. That is the normal distribution and everything's fine. You proceed like normal. If you have fewer than 30, maybe 6 people in your sample, then that normal distribution gets skewed and it looks like the purple line. I don't know how well you can differentiate these colors, but it looks like the purple graph. And if you have only 3 people, the normal distribution gets skewed even more. And if you have 2 people, it's skewed a tremendous amount. And what's being skewed not only is the curve, but the area, i.e. the probability, right? That's why this is important. So a bunch of really smart people went out and they did areas under the curves for all these different graphs, and they put them in a table. Now, this table would be like 50 pages long, right? So they only did certain values, which is a limitation to looking this up in a table, which is why we're going to use technology to get the exact answer for any n and any target, okay? So once you have all this, here's how you put it together. So first of all, you want to state your variables. So X is the random variable and mu is the mean of the random variable, right? And these are for, let's see, X is going to be the sample and mu is going to be the population. Okay, and I think we established that like a long time ago, that the sample is going to use like X, Y, and Z, and the population is going to use Greek letters like mu for the mean, okay? So we're going to check and state the assumptions for the hypothesis tests are met. And basically, is it random? Yep. Now, if the sample size is less than 30, we're going to use a t-test. But if the sample size is greater than 30, then we can just use a z-test, or you can still use the t-test because the numbers are the same. It doesn't matter. So here's how we're going to find the information. We're going to locate our point estimator, the mean of our sample, okay? And then we have to indicate our sample size, and then we're going to calculate our margin of error, which if our number of values is, or our number of items is greater than 30, we're going to use the z-score. So this is n is greater than 30. If the number of items is less than 30, then we have to use the t-score, okay? And so then once we calculate this margin of error, we add it to the mean to find the upper bound, and then we subtract it from the mean to find the lower bound, and we're done. And so then what we do is we make a statement saying this interval contains, there's a 95% chance that this interval contains the population mean, the true mean of the population. Okay, so here's an example. And we've got 2 examples to go through, and then we're done. And then that's it for this section. So in this example, you'll notice that the number of items that we have are greater than 30. So we're going to use a z-score, okay? So this is the life expectancy of 53 random European men in 2011, okay? And we want to find a 99% confidence interval for the mean life expectancy of all European men. Okay, so we want to know in 2011, what is the life expectancy of all European men? Clearly, we can't do that for every single European male. And so what we're going to do is we're going to get a sample of 53. We're going to have a 99% confidence level, and we're going to find a margin of error. Then we're going to add and subtract that margin of error from the average of our 53 to give a confidence interval. So from this data set, what we need is the mean and the standard deviation. Okay, so we take our data set, we throw it into a spreadsheet, and here's where we find the count and the formula for the count, right? This is the mean, and this is the standard deviation. Okay, great. These are all things we've done before. Here's the confidence interval that I want, 99%. Remember, that's the area of the normal distribution. So the mean and the standard deviation establish our curve. And then this confidence level establishes the boundaries and the area that we're trying to find. Okay? So once we know the confidence level, we also know alpha. And alpha will be the area below the curve. This is going to become important later on. It's not so important right now, but it's pretty important later on. And then here's our degrees of freedom. So here's how we calculate the t-score, right? Not the z-score, but the t-score in this case. And you use this formula. So you put in your value for alpha. That's the 1.0. Remember, we said we'd use that. So here it is. And then you also put in your degrees of freedom. And the spreadsheet will go out and calculate the area, or pardon me, not the area, but the number of standard deviations away from the mean that t-score is. So that means this mark right here is 2.67 standard deviations above the mean and 2.67 standard deviations below the mean. Okay, we use that value, that t-score value, right here. And then we multiply that by the sample standard deviation and divide by the square root of the number of items that we have, and that will give us our margin of error. We then take that margin of error, which is 2.1, we add it to the mean. So 73.74 is our mean. We're going to add 2.1038, and we're going to subtract 2.0138. And that will give us our upper and lower bound. And so half of these calculations you've done before. You've seen them before. I'd actually say more than half you've done before. These are the new calculations that you have to learn. How do you get the t-score and how do you calculate the margin of error? And the formulas are given, and the formulas are somewhat familiar. You've already seen the standard deviation divided by the square root of the numbers. The only difference one right now is this t-score. That's the only thing that's new. Okay. And then what you do is you write a summary. So we can say, and here, by the way, is all the steps that we just did, walking through all these calculations if you wanted to do it by hand instead of using the spreadsheet. And then what you can say is that there is a 99% chance that this interval from 71.6 years to 75.8 years contains the mean life expectancy of all European men in 2011. That interval, you're 99% confident that if you were to go out and sample the entire population, that the average male lifespan would be between those two intervals. Okay, the last example is what you do if you have a confidence level that is less than 30. And basically, it's the exact same thing. It's the exact same thing. So you can go out to this website and you can find, this website lists the reported IQs of celebrities. So you can go out and find 20 celebrities and write down their IQs. Now, what's important to notice here is that we've got 20 celebrities. So N is less than 30. So we have to use a t-score in this situation. Our normal distribution curve is now being modified. And now probably looks something like that, like the blue curve, okay? So if N is 20, we probably get a curve that looks like this, which means we can't use a z-score. We have to use this modified t-score. So we take our data set, we plug it into a spreadsheet, and we find the mean, and we find the standard deviation of our 20 celebrities. And note that we're looking for a 98% confidence interval. That is going to impact our t-score, okay? So here we go. We go out and we do the 20 IQ scores. We find that the mean of our sample is 145. We find the standard deviation of our sample is this. We know our degrees of freedom are 19, one less than the number of items, and our confidence level is 98%. We also know from this that alpha is equal to 2%, okay? So now we go out to our T table and we look up the degrees of freedom are 19. So we look up 19 and then we find the 98% confidence and we follow these across, boom, boom, and we find a t-score of 2.539. So that's our t-score. That's how many standard deviations away from the mean 98 percentile is, or the ends of the 98th area, okay? So now that we have this t-score, we're going to plug that in here along with our standard deviation and our value for N, right? These are all values that we got from earlier, and we calculate our margin of error to be 16.6. So the t-score is not the end calculation. The t-score is used to help find the margin of error. Okay, so remember that. Once you find the t-score, you've got to go one more step to find the margin of error, which is multiplied by the standard deviation divided by the square root of the number of items there are. Once you have this margin of error, it's pretty much all downhill from there. Pretty easy to calculate things because you're going to take that margin of error, you're going to subtract it from the mean, the sample mean, and you're going to add it to the sample mean, okay? And then that is going to give you your interval. So you could say that there is a 98% chance, you are 98% confident that if you were to go out and measure the IQ score of every celebrity, it would be in this interval, where this is your lower bound and this is your upper bound. So here is the 7.2 tech tool, and check this out. So what you put in here is you put in your sample size, you put in the sample mean, you put in the sample standard deviation, and then you put in your confidence level as a decimal, okay? So 0.98 for 98% confidence. This is the IQ stuff that we just looked at. The tech tool then automatically calculates the degrees of freedom, and here's the formula that I use to calculate that. Here's the t-table, the t-score, the critical value from the t-score, and this is the formula that we use to find that, TINV. And then this is the margin of error. And to find the margin of error, we took the t-score multiplied by the standard deviation divided by the square root of the number of items that we have. Once we have the margin of error, we subtract it from the mean, from the 145, to get the lower bound, and then we add it to the mean to get the upper bound, 161. And this is your interval. And what's cool, I think, about this is that you can change this and you'll see the intervals automatically change. So remember when I said your confidence goes up, the interval gets larger. So this is 128 and 161. Let's make our confidence level 0.999. And I'm going to hit enter and watch. The interval is going to increase. The lower bound is going to get lower and the upper bound is going to get upper, higher. Okay, ready? Here we go. 3, 2, 1. So you saw the lower bound went from 121 down to 119, and the upper bound went from what, 168 up to 170 or whatever it was. And if I make this confidence level lower, the interval will get smaller. Okay, so if I make it 0.5, you'll notice this will be very dramatic. That 119 is going to go up. That lower bound is going to increase, and the upper bound is going to decrease. Ready? Here we go. And look at the margin of error, by the way, 25. Okay, 3, 2, 1. Now my margin of error goes down to 4. So I have a very small margin of error, and look how tiny this interval is.